everyone, and welcome back to Part 2A of our journey into chemical reactions and equations. In our last session, we saw chemistry happening all around us, right? Well, today, we're going to learn how scientists actually write all that amazing stuff down. Let's get right into it. So, think about it. Last time, we talked about all these chemical changes, like iron rusting or food being cooked. But if you had to write out a full sentence to describe every single reaction, wow, that would take forever. How do scientists communicate these complex ideas quickly and efficiently? There has to be a better way, right? You bet there is. And that's our mission for today. We're going to take those long descriptions and turn them into something much, much simpler. This is the very first step toward writing a proper chemical equation. Okay, let's start with that really cool experiment from the textbook. You know the one. Now, describing it like this, when a magnesium ribbon is burnt in oxygen, it gets converted to magnesium oxide. I mean, that's totally accurate. It tells us everything that happened, but you can feel it, can't you? It's just a little bit long. Exactly. It's way too long. In science, we love efficiency and precision. Writing out huge sentences for every reaction just isn't practical. So chemists developed a much cleaner, shorter way to get the point across. And this is our introduction to something called a word equation. So what is a word equation? Well, it's pretty much what it sounds like. It's the simplest way to show a chemical reaction just by using the names of the substances. No long sentences, just the key players. And look at that. That whole long sentence we had before, it boils down to this clean, simple line. Magnesium plus oxygen gives us magnesium oxide. So much better, right? Now let's actually break down what each part of this thing means. Believe it or not, chemical equations have their own grammar, just like a language. There are different parts that tell a story. So let's take a closer look and understand the anatomy of this equation. All right, so every reaction basically has a before and an after. On the left-hand side, we have the reactants. These are your starting ingredients, the stuff you begin with. In our case, that's magnesium and oxygen. Then on the right-hand side, we have the products. This is the new stuff that's formed during the reaction. Here, it's magnesium oxide. Just remember, reactants on the left, products on the right. Simple as that. Now, what about those symbols in the middle? Well, the plus sign is easy. It just means and or reacts with. So we can say magnesium reacts with oxygen. Now that arrow is super important. It always points from the reactants to the products, showing us which way the reaction is going. You can read it as to form or to yield. So the whole thing reads like a sentence. Magnesium and oxygen react to form magnesium oxide. See? It's a whole language. Okay, time for a quick check-in. It's your turn. Using what we just learned, what would the word equation look like for the reaction of zinc with dilute sulfuric acid, which produces zinc sulfate and hydrogen? Go ahead, pause for a moment and give it a shot. Did you get it? It's zinc plus sulfuric acid, arrow, zinc sulfate plus hydrogen. The reactants, zinc and sulfuric acid, are on the left, and the products, zinc sulfate and hydrogen, are on the right. If you got that, awesome. You're already thinking like a chemist. Okay, so word equations are a great start. They're way better than long sentences, but scientists all over the world speak different languages. How do we make sure a chemist in Japan and a chemist in Brazil are talking about the exact same thing? We need to take it one step further and make our equations truly universal. So the question is, can we make this even shorter, even more scientific? Can we create a language of chemistry that everyone on the planet can understand, no matter what language they speak? Oh, absolutely. To do that, we simply swap out the words for their official chemical formulas. It's like a secret code that everyone knows. So magnesium becomes Mg, oxygen becomes O2, and magnesium oxide becomes MgO. This is what makes chemistry so powerful and universal. And just like that, our word equation transforms into this. Mg plus O2, ba-bum, MgO. Now that looks like something you'd see in a science lab, doesn't it? It's short, it's precise, and anyone, anywhere can understand exactly what it means. Now, this kind of equation has a special name. We call it a skeletal chemical equation. Think of it like the basic skeleton or the blueprint for the reaction. It tells us which substances are involved, but it might not be telling us the whole story just yet. And that's a little clue for where we're headed next. So we've come a long way, right? From a full sentence to a word equation and now to a sleek skeletal equation. But before we wrap up this part, I want to leave you with one little puzzle to think about. Let's look at our equation one more time. Mg plus O2 arrow MgO. Look really closely with me. On the left side, the reactant side, how many oxygen atoms do we have? We have 2, right, in that O2 molecule? Okay, now look at the right side, the product side. How many oxygen atoms are in MgO? Just 1. So we started with 2 oxygen atoms, and we ended up with 1. Where did the other one go? Did it just disappear? Is this equation really complete? And that question is the perfect place to stop for today. We're going to solve that mystery of the vanishing atom in Part 2B. That's when we're going to get into the super important concept of balancing chemical equations to make sure everything adds up perfectly. So that's our journey from a sentence to a skeletal equation. Was this clear for you? Let me know down in the comments. And of course, if you have any doubts at all, just ask. Thanks for joining me, and I'll see you in Part 2B to solve our little atom mystery.